Hello, now we'll be going into question 2. Hopefully you have gone through the question 1 videos because those are very helpful ones because there's also a stack of mark through where the lecturer, Miss Lee, will go through all the student samples and just mark and see. Okay. Question 2 is a little bit of a different animal or different question. The focus, like I mentioned earlier, is not so much on your manipulation, presentation data. You don't draw graph, Yeah, those of you who don't like graph. But the focus is more on the analysis and evaluation. Wow, look at that. So you will have to be writing sentences, sometimes essays. No, don't write essays. But we'll go through every single step on how you can do well in paper 3, question 2. But I will not go through very much on the data part because it's largely the same rules. Your SF, your DP, take average, must write average, show your working. Those kind of stuff already done in question 1. So I'm going to focus more on 3 main ideas for question 3, main skills. Today's first video will be about estimating uncertainty. Oh, uncertainty. We are very uncertain about uncertainty. And it's actually quite subjective lah, okay? And then the second video that we'll look at, the next one, will be about hypothesis, testing hypothesis. We will see what is that in a second. Hypothesis. And the last and final one, we'll talk about suggestions and limitations. So that's the part where you kind of write sentences lah. So limitations and suggestions. Limitations, suggestions. What it means is, what was the problem you faced in your experiment that prevent you from getting good data? And how are you going to fix it? Okay, so let's take a look at today's first part on estimating uncertainty in experiments. Let's look at this terminal velocity lab as an example. Oh, this is a good one. Also, by FYI, paper 3 question 2, usually the experiment got a lot of uncertainty one. It's like very hard to get precise values, but that's okay. They're not asking you to draw graphs, so don't worry about that. Let's see what this thing's about. Object falls in air, it got drag force, and it will reach terminal velocity. Okay, so we're looking at the relationship between terminal velocity and the diameter of the cone. So they'll ask you to cut a filter paper, tape together. This is the cone. So once you have a cone, you put it very high up, then you drop it, then it falls. And then you take the time. How long does it take to fall from the top of the ruler to the bottom of the ruler? Here you take time. How long it takes. That's all it is. Oftentimes, question 2 can be easier than question 1 in setup. Not necessarily, sometimes. But generally, it's a lot of uncertainty. I see here you want to time stuff, also very hard. So, they ask you to measure diameters, record measurement. Okay, and then you see this part. This is the one I want to focus in on. Estimate the percentage uncertainty. Ooh. Then calculate other stuff, blah, blah, blah. And then they ask more standard stuff. Okay, so let's just go through this part and then I'll go to how you can estimate uncertainty. Let's go through the mark scheme first. Refresher of question 1. Measure record diameter of cone, 13.5 cm. Okay, that's okay. But if you actually try to measure the diameter of a paper cone, you just take a random piece of paper, roll into a cone, something like that. Then you try to measure diameter. It's a bit hard because your cone is squishy, and then it moves around a bit, and then, those kind of thing, you want to take into consideration because you can use that for the suggestions and limitations parts later. So you can make a note as you're going through this. You say, it was hard to do or hard to measure something accurately. What is accuracy? Accuracy is how close you are to true value. This is your true value, but you measure already, may not be the actual diameter, or maybe your cone is like a bit out of shape. So what actually is the true value? We don't know. But I recommend, although they say only one measurement, right? If you can, try take a few and then find average. That will help to, take into account the variations. For example, you measure diameter from here to here. Then you measure diameter from here to here. Measure diameter from here to here. Many diameter already, you find average. And don't forget to write out your working if you do that. But this one, they're still not too strict about this because they assume diameter okay lah. Okay, so mark scheme, I'm going to leave it on the right side, these ones. This mark scheme is all over, so I just cut and paste little bit. First value of D nearest to cm or mm, 1 mark. Check and see. Ruler must measure to 1 mm, so you must have this decimal. Otherwise, like in question 1, wow, minus, lose mark already. So, okay. This one's okay. Then we come down to what else? Oh yes, you need to measure the height. That is your independent variable. You choose what height you want, and then your time is your dependent variable because it will change depending on what height you choose. So here, right here, you choose height. Height, hopefully straightforward. Okay, you got your 0.0, that's good. And here they give you 1 mark for T. Because H, they assume you just choose lah, okay. T, they have a criteria here. First value must be between 0.1 and 10 seconds. Check and see. Correct. Can. And you must have repeated measurements. Oh, this one, they want repeated measurements already. First or second reading. There's 2 readings, by the way. So, got repeated measurement. Good. Don't have. Also, best to also show if you have T, do a few times. So, T1, T2, T3, take average. Better, because timing, a lot of uncertainty. So, better to do that. So, here's just 1 mark. And if you're wondering, why got criteria here one? Always this answer? No. Paper 3 question 2, their mark scheme will change depending on the question. So in this case, it is reasonable to have 0.1 and 10. That's why they give you a accepted range lah. If it's beyond, then they know something wrong with the experiment already. Maybe you forgot to press stop on your stopwatch, or who knows what happened. Okay, so they will often give a reasonable range. If you do things logically, you should have no problem with that one. Okay. So, all right, missing repeated measurements. Oh, sadness. So, if you can, you just repeat everything lah, measure a few times. See, average diameter, average time. Okay. Then they ask you to do the same thing again, repeat. But here, we come to this point where they say estimate the percentage uncertainty in T. How do you estimate percentage uncertainty in T again? Well, to remember, you are measuring time with a stopwatch, right? Tick-tock. And oftentimes we say use the smallest division of the stopwatch, but you have to think of time as heavily affected by human reaction. So yes, you have maybe you have a smallest time of, what's the smallest time? Smallest division of this stopwatch is 0.01 second. Wow, very small. But your human reaction time is already 0.2 to 0.5 second. So if this one is bigger than your smallest division, then you choose the bigger one. It's okay to use a bigger uncertainty than a smaller one. It's better to overestimate lah. And also they say estimate, right? So there's no fixed rule, not like a fixed rule to it. So you need to estimate. Let's see what's the allowed range for this one. They give a range. Absolute uncertainty, means in the 1 second, must be 0.1 to 0.5 range. Okay, so if you choose what this person choose, 0.2, okay, it's a bit on the low end, but okay. Or if repeated reading has been done, then you can do half the range. That is, if earlier you find T average, the other way is you can find half the range of all your readings from T. So like T1, T2, T3, add together. Okay, you can find the range of that. And of course, you find percentage, everything. Okay, this one looks good. 0.2 out of the measurement times 100. Okay, this times 100. This is the ratio. This one to convert to percentage, you get 21.3. Okay lah, can. So I'm going to go through to the end very quickly just so you can see. And then we'll go back to percentage uncertainty. Calculate terminal velocity. Mark scheme say must calculate correctly. Normally, examiner will check how to find velocity. You take distance divided by time. Okay, straightforward lah. Calculate correctly, okay already lah. One note to take into consideration. You are calculating V. So this is your calculated value. So you must, like in paper 1, question 1, you must follow the SF or the least SF of your raw data. So your distance just now was what? H, okay lah. 100, don't know, many SF there. Could be 2 or 3. Time, you have 2 SF. So you can put 2 or 3 SF lah. 2 SF or 3 SF. Can. Okay. Cannot be less than 2 or 3. Okay. Can. Then what happened next? This person have to cut a bigger one. So your cone now is smaller. Smaller cone. And then do the same thing. Drop the thing, measure. They will, in paper 2, they'll ask you to do 2 different variations. One with bigger cone, one smaller cone. But it depends. Different experiment, yeah? So they say repeat everything. So you repeat everything. And you see, okay, diameter, height, time, decimal placing, okay. Second value of D must be less than first value. Of course, you cut away a bit of the cone, must be smaller. Hey, check and see, 10.2. The first one is what? 13.5. Okay, good. Can. Pass. 1 mark already. So this one is about common sense one. 2 values of H. Oh, okay. Previously you choose 100. Now also 100. Okay lah, can lah. Second value of T. Yes, you did do a second value of T. Second value of V. Calculate correctly. Okay, I assume you calculate correctly. Done. So this one is like 3 marks. As long as you do, okay already one. Question 2 very chill one. Okay, that's all. Last one. Quality of data. This is from data quality section. A smaller d gives a greater v. So to summarize, I'm going to do a table so you can see or not, see whether your trend is correct or not. This one looks at the trend. The second value you did 10.2 cm. Then your velocity is 1.33 meters, meters per second, cm. You should put the units in top. This one is no need. You don't have to draw this one. This is just for you to check your trend. For me to check my trend. Okay. What's the first one? Diameter 13.5 and 1.06. So 13.5, 1.06. So here you will check and see. A smaller d means a greater v. So this one is smaller d, greater v. Check, correct. Okay, done. Data quality done. Wow, very easy compared to paper 1. You will check so many things. Trend. Okay, now that's the first part. Pretty much the same. You record, you measure. The only new thing here is estimate percentage uncertainty. So now let's take a look about how you can estimate percentage uncertainty, not just for timer, but for like all kinds of stuff. Okay, let's go and see. Here I'm just going to walk through some of the common ways you can estimate uncertainty. Just remember the word estimate. CIE, they're like, usually they don't care exactly how you get your uncertainty as long as you estimate it. So for all you know, you could just come up with a number, and if it's within an acceptable, reasonable range, then they're like, okay lah, can lah. But for some of you who prefer something more structured, here's a way to think of it. Okay, so I'm going to look at this pocket guide. So first one, we're going to build up on your chapter 2 knowledge on uncertainties. You don't have to worry about this, these absolute uncertainty rounding because it's not in paper 3. But some of these are helpful. Okay, so first thing, single measurements. If they're analog means no electric. It's like ruler, all this thing, scale, the scale, point here, point there one. When you are making analog instrument readings, you want to take half the smallest division as the uncertainty for a single reading. Okay, this is for single reading. But I'll explain how you have to take a little bit bigger later. Okay, anyway, this is the basic the minimum. Minimum you must take a single minimum uncertainty of single reading. Half smallest division. But ruler is a very interesting case because ruler, when you're trying to adjust, let's say this W thing here, you're actually doing 2 readings in 1 measurement. So you put your eye here to see, that's 1 reading. Then you put your eye here again to see, there is 2 reading. So while you're making 1 measurement of W, there's 2 reading. So here got plus minus, what's the smallest division here? 0.1. Okay lah, this ruler is 0.1 cm. 0.1 cm. Then this first reading, you got plus minus 0.1 cm. So in the end, you will have 0.2 cm as your uncertainty for this one measurement, because there's two reading. Reading is basically how many times your eye go and look there. So here, one eye, here, two eye. You look. Oh. Different things like scales, it's like those type where it's got a needle here and then you like that. Usually after you put your whatever thing you're measuring, the scale deflect, you put your eye here, you look. Okay, so that is plus minus half smallest. Because your eye only look one time, here your eye look two times, so two reading instead of only one reading. Okay, so that's one way you can estimate the uncertainty of this thing. So like that. This very ngam, just nice, is the smallest, is rated to smallest division of ruler. Okay, so here yellow 2, 4, 6, 8. So very ngam is also smallest division. Although each one is half smallest and half smallest, this one turned out to be smallest division. Now, when you're actually in paper 3, it's okay to use a bigger estimate of your whatever length you're measuring. For example, I say I have a calculator here. I want to measure the width of the calculator. I take a ruler, I put like that. Where's my ruler? Like that. Okay. So, I will measure. I say, oh, measure. This is how long? I cannot see. Maybe I measure the thing is 7.5 plus minus smallest division of this ruler is like the labs one, so 1 millimeter. Well, actually, yeah, like 1 millimeter. So I just, okay, 0.1. Okay, sure. So I'll be happy and say, okay, yeah, done. But in real life, the uncertainty is a little bit more than that. Because you look at this calculator, it's not a nice cube with straight edges. So maybe the shape makes it a bit hard to measure exactly 7.5. So what you could do in experiment is, you see roughly how big you want your uncertainty, you just choose something a little bit bigger, something reasonable. So maybe in experiments in paper 3, you say plus minus 0.3 lah. It was very round shape, so it's hard to tell what was the thing. So here it's okay to overestimate a little bit from your smallest division. This one is smallest division. Okay, so it's the same thing for any kind of analog instrument. When you're measuring lengths, especially, you do a lot of lengths. Try to think how hard was it to measure your thing, and then you can choose a number that's a little bit bigger. Okay, sometimes you may prefer something more concrete. Say, Miss, I don't like this, choose. I don't know what number to choose. Okay, you don't know what number to choose, then you take repeated measurements. You take the calculator, you measure 5 times. 1, 2, 3, 4, 5. And then you see what's your measurement each time. Okay, so first time I measure. Okay, now 7 point. My eye problem a bit, 7.7 lah. So maybe I say 7.7. Then I measure again, I look, okay lah. Maybe I move it out a bit because the calculator's a bit round. 7.678. Okay lah, 7.8. Then it's a bit round, so maybe I take the smaller one. 7.6. So that's what it means by repeated measurement. You measure the same thing a few times. Alright? So because they are different values, you see they are a bit different, you need to find the range, half the range. So in this case, my uncertainty will be plus minus half of the range. What is the range? Oh, this one you have to think of maths a bit. Range is your biggest, what's the biggest value? Biggest minus the smallest. Okay, so 7.8 minus 7.6 divided by 2. So what is the range here? So that will be 7.8 minus 7.6. Very small, 0.2. So 0.1 equal to plus minus divided by 2. It was 0.05 cm. So small. Sure not. So when you try this, you see 0.05. Then you look here. That's smaller than your smallest division already. Cannot be. So what you do, you choose the bigger one. So this one seems too small. So okay lah, you choose the bigger one, choose this one. Or even better, choose this one. Okay, so for anything, you can try estimate, you can do repeated measurement and check. But if it's smaller than your small division, something wrong already, okay lah. Don't choose this method. But whether you choose this one or you choose this one, it's really up to you. It's estimating only, so there's no like fixed correct answer. As long as you're in a reasonable range. Okay, so that's for analog instruments. Same thing for vernier scale, micrometer, all this kind of scale thing. How to draw a micrometer? Like that. C shape. Something like this. And then you have the vernier caliper, like that. Okay lah, you just use smallest division, estimate, choose a bit more if it was hard to measure your thing. They're very generous on this thing. Okay, then you come to digital instruments. Everything you see got a screen, got number, got things flashing. That's a digital instrument. So what you can do is, you just choose the least significant figure. So you see here, this mini voltmeter, 2.97 millivolt, right? You could say, oh, smallest is 0.1 millivolt. So I choose that lor. Can? This is the minimum. But, in real life, you may notice when you're trying to measure voltage or air current, your number will actually jump up and down a lot. So maybe one moment is 29.7. Suddenly it jump up to, 29.8. Then suddenly it's 29.6. Suddenly it's 29.5. That's an uncertainty already. It's bouncing up and down. So oftentimes it is good to choose something more than your smallest division. This is the minimum lah. But what I would do is, you just see 29.7 plus minus, bounce up and down. You can do the range thing again, half the range. But if you're lazy to do that, you see, smallest 29.5, biggest 29.8, plus minus 2 lah, so 0.2 millivolts. Choose something bigger, it's okay. If your values are jumping a lot, choose something even bigger. So again, repeating, this is estimating only. This is the experimental skill. You need to know how uncertain you are when you're trying to do stuff in lab. So you look, wow, my voltmeter jump up and down. Okay lah, I choose a bigger uncertainty. That's fair. Okay, you can overestimate, do not underestimate. Now, the special one that the CIE is more picky is time. Time, you measure with stopwatch. But if there is a known larger uncertainty that you know for sure, such as human reaction time, we know, is 0.2 to 0.5, I put on average. So although your clock's smallest division is 0.01, you might want to definitely choose something bigger than 0.01 because impossible, you are so precise. Okay, your human reaction, your brain very blur. So choose something here lor. So here I choose the minimum. Or if you feel on that day when you're doing experiment, your brain was very sleepy, choose something bigger lor, plus minus 0.4 seconds. That is fair. It's a good estimate. If you're wondering, Miss, where this human reaction time come from? Why got human reaction time one? Because we are humans. This is our brain. Yeah, how to draw brain? Mouth, brain. Okay, brain. When your eye, you see the thing, the signal will send to your brain. And then the brain will send the signal to your hand and say, hey, stop the timer. So this whole pathway going from your eye to your brain and to your hand, that is the human reaction time. And everyone's human reaction time is different. Some people, if you play sports, you play a lot of games, generally your human reaction time is faster. So 0.2, 0.5. You need to take this into account. Okay? And sometimes it helps to, when you're doing something that is related to time, there is this technique called multiple measurements. Okay, so we know one measurement, your uncertainty is already 0.2, 0.5. So let's say you are trying to time a spring that is bouncing up and down. Doing, 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 doing. Go up and down, up and down, up and down. And you want to find one oscillation, the time it go up and come down. What's the time? Sometimes it's very short. So it actually maybe one bounce is only 0.4 seconds. On the stopwatch it says 0.4 lah. But then your uncertainty of human reaction is already 0.2 to 0.4. I'll say, okay, general 0.2. That's not good. Can you see why? Your uncertainty is so big. Your measurement is so small. So your percentage uncertainty is, let me calculate for you, 0.2, 0.4 times 100. So 0.2 divided by 0.4 times 100. Wow, 50% uncertainty. Woo! That is very, very big. So sometimes certain techniques is, if there are oscillations, you don't find one oscillation lah, you find 10 oscillation. And then later you can divide by 10 oscillation. So let's say maybe you say one oscillation very hard, too fast miss, cannot time, my eyes not fast enough. So okay, you do 10 oscillations. So 10 oscillation, maybe your time is 12.6 on the stopwatch. Then your uncertainty in measuring that 10 oscillation is only 0.2 because you click only one time. Okay, some of you say, miss, I start and then I stop. So there's 2 times. Okay, sure, then you do 0.4 uncertainty. But anyway, here, you're measuring 10 oscillations. So you check the uncertainty percentage. This is 0.2 over 12.6 times 100. What is that? 0.2 divided by 12.6. Much smaller. Now your uncertainty become 1.5, 1.6% only. So this is much better. It's called a good experimental technique. If it's hard to time something, make your time longer. Then your uncertainty is still the same small one, but your percentage uncertainty will be much smaller. Okay, so whenever you see experiments with time oscillation, repeating one, do more oscillation, 10 times, 20 times, 50 times, within reasonable range. Okay, so that's on how you can deal with many oscillation divided by time, only for oscillations. Okay, so that's the whole bit about uncertainty and things like that. Yep. So hopefully when you try estimating stuff, don't be too afraid to estimate it a little bigger. It's okay to estimate a little bigger. And of course, these are just guidelines for the minimum. If you use smallest division, that's the minimum you can go. Okay, so let's go back to the students' work in the lab report. See, the fellows choose 0.2 as the uncertainty. Okay lah, can lah, 0.2 within human reaction time. Even the marks team also say okay. I have one student say, miss, my timer, I need to hit start. So got a 0.2 already. Then I need to hit stop again. So there's 2 0.2s. You could think of that. So 0.2 plus 0.2, you can use uncertainty of 0.4, which is why they allow this range. This one is when you hit start, when you hit stop. The point is, you estimate can already. No need so precise. Okay. So that's all for this first part. The next part, we will be using the uncertainty we estimated here, very importantly, to come to conclusions on a hypothesis that the experiment will ask you to test.